In the previous lecture, we discussed the overview of strength of materials. In the present lecture, we will discuss the concept of simple stresses and strains. When a structural member or a body is acted upon by external force or load, then internal resisting force is set up within the body. Such a body is then said that it is in the state of stress. Let's consider bar AB is subjected to axial forces capital P at the ends, and let's consider capital A is its cross sectional area and capital L is its length. Now we have to set that bar AB is in the state of stress. So now stress is defined as it is the resistance force offered by the body against to the deformation. So stress is the resistance offered by the body to the deformation. In order to know the internal stresses produced in the bar, consider a section MN normal to the longitudinal axis of the bar. So here MN is the cross section of the AB bar, which is normal to the longitudinal axis. If we consider the equilibrium either part of the left part as well as the right part at the section MN, take in the free body diagram, then internal resistance of stress, that is sigma, offered by the molecules against to the external force, it is assumed to be uniformly distributed, so over the whole cross sectional area. So now it is we are calling as the internal resistance of stress. This is the internal resistance of the stress. So now we have to say that when the stress equal to the internal resistance per uniform cross section. So here we are using the notation is the sigma, then sigma stress equal to the P divided by A. So here P is the internal resistance force divided by cross sectional area normal to the axis. So don't say that one stress is not a force divided by area. So stress is the ratio of the internal resistance force to the cross sectional area, and stress is act in a direction perpendicular to the cut surface. It is referred as the normal stress. So stress is perpendicular to this cut surface, and units of the stress is resistance force, that is the newtons, divided by cross sectional area units is the mm square, then stress units are the Newton divided by mm square. Next we look for the units of stress. First we have to see in the SI system. In SI system, units of stress is Newton per meter square or the Pascal. In general, force is expressed in the terms of kilonewton or meganewton, and we know that when the 1 kilonewton equal to the 10 cubed Newton, and 1 meganewton equal to the 10 to the power of 6 Newton, and 1 giganewton equal to the 10 to the power 9 Newton. Let's see how to convert the Newton per mm square into the megapascals, and we know that one Newton per mm square equal to the 10 to the power of 6 Newton per meter square, and Newton per meter square is equal to the Pascal. Then Newton per mm square equal to the 10 to the power of 6 Pascal, which is equal to the 1 megapascal. So Newton per mm square equal to the 1 megapascal or 1 MPa. So next we have to look for the units in the MKS system. So in the MKS system, unit of force equal to the gravitational unit, that is the kilogram force or kgf, and in general we are expressing in the terms of the tons, and 1 ton equal to the 1000 kg. Then the unit of stress in the MKS system is expressed as kg per centimeter square, that is 1 kgf equal to the 9.807 Newton, which is nearly 10 newtons. Then 1 kg per centimeter square equal to the, so have to 1 kg equal to the, so 10 newtons. So 10 Newton divided by centimeter square have to convert into the meter square, then 10 to the power minus 4 meter square. Then 1 kg per centimeter square equal to the 10 to the power 5 Newton per meter square, which is equal to the 10 to the power 5 Pascal. So 1 kg per centimeter square equal to the 10 to the power of 5 Pascal. So next different kinds of stresses are there. So that is the normal stress. So normal stress is subclassified into the tensile stress and compressive stress. And second one is the shear stress or tangential stress. Third one is the bending stress. Fourth one is the twist or torsional stress. And last one is the bearing stress. So in the present lecture we will look for the normal stress and the shear stress. So first we have to look for the normal stress. When a stress acts in the direction perpendicular to the cut surface, it is known as the normal stress. So this normal stress is the subclassified into tensile stress and the compressive stress. So now I have to look for the tensile stress. When a body stretched by the force capital P, the resulting stresses are tensile stresses, which means if there is an increase in length or extension of the body in the direction of force applied, the stress setup is called as the tensile stress. Let's see the diagram. So here we are applying the capital P force. It is causes for the increasing in the length or maybe extension of the body in the direction of the force applied. So these type of stresses we are calling as the tensile stresses. Then the tensile stress exists between two parts of a body when each draws the other towards itself. Then when a body is stretched by two equal forces applied to the normal to cross-sectional area, the restoring force per unit area in the body is called as the tensile stress. Then tensile stress equal to the applied force, so capital P, then internal resisting forces also generating the capital P. So now tensile stress equal to the internal resistance force capital P divided by its cross-sectional area capital A. So next we have to look for the compressive stress. If there is a decrease in the length of the body or compression of the body due to the force applied, then the stress setup is called as the compressive stress. Let's see in the diagram. So we are applying the compressive stresses. So these are the caused for the decreasing in length or compression of the body. So in this condition, so developed stresses we are calling as the compressive stresses. Thus compressive stress exists between two parts of a body. Each pushes the other from it. Such a state of stress is shown in the diagram. So here I have to observe the state of the compressive stress. Then compressive stress equal to the resistance force capital P divided by its cross-sectional area capital A. So next we have to look for the shear stress or tangential stress. When a deforming force acting tangentially to the surface of a body produces a change in the shape of the body without any change in volume, The stress set up in the body is called as the shear stresses. So shear stress is one which acts parallel or tangential to the surface. Let's see in the diagram. So here we are applying the parallelly force we are applying to the surface. So in the surface we are applying the parallel force is applying in the parallel to the surface. Then shear stress exists between the parts of body when the two parts exerts equal and opposite forces on each other laterally in direction tangentially to their surface in contact. So here you have to observe. So two forces opposite in direction. So these two forces are applying the tangentially to their surface contact. So best example of the shear stress is riveted connections. Now let's consider if a shear force capital P applied on the top face of area capital A of a cubical body whose bottom face is rigidly fixed, then changes the shape of the cubical body without changing its volume. Then shear stress we are representing in the tau equal to the P divided by the capital A. So next we have to see for the strain. So previously we discussed the stresses. Now we have to look for the strain. Generally we are representing in the epsilon. So let's consider when a prismatic bar is subjected to axial load, it undergoes a change in length. This change in length usually called as the deformation. So when applied the load on a prismatic body, obviously body will go to it's a deformation. So deformation means a change in the length. We are calling as a deformation. So let's consider here. So if the axial force is tensile, then the length of the bar is increased. See in the diagram have to see. We are applying the forces capital P. Nature of the forces is the tensile forces, and the deformation will be occur. So the deformation is change in length. So due to the tensile forces, length of the bar is increased. Let's consider the length of the bar is increased is delta. Similarly, you have to look for when the axial force is compressive, then the length of the bar is decreased. See in the diagram, here we are applying the compressive forces. So due to the P, due to these compressive forces, the length of the bar is decreased. That is, let us consider delta. Delta is decreased. Next strain is the deformation per unit length of the bar is termed as the strain. So it is represented by the epsilon or E. Then epsilon equal to the deformation. Let's consider delta is the deformation divided by its original length. So strain epsilon equal to the delta by L. So in the tensile strain, increase in length. So here deformation, that is the delta equal to the increase in length divided by original length. And in the compressive strain, compressive strain. And in the compressive strain, length will be decrease. So compressive strain equal to the decrease in length divided by the original length. And units of the strain is, there is no units. So deformation is, generally we are representing in mm. So length also we are representing in the mm. So mm by mm there is no units. So for the strain is, there is no unit. So it is very important. So for the strain there is no units. Next we look for the shear deformation. So let's see in the diagram. So here we are applying the tangential forces on the top surface and the bottom surface. Let's consider P. Then deformation it will be occur, that is the delta. Let's consider length of the bar is capital L. Then this shear deformation. So tan phi. So tan phi equal to the, so delta divided by L. So then this value is nearly equal to the, so tan phi value is the very small, so then we have to consider the phi value only. Then phi equal to the, that is the shear deformation equal to the delta by L. So these are the concepts of simple stresses and strains, and thank you.